Hello, my name is Andrew Gary, and welcome to Seismic Sound-Off, in-depth conversations in applied geophysics. In this episode, I speak with Nimisha Vedanti about her honorary lecture on understanding seismic wave attenuation mechanisms. Nimisha explains how she discovered the problem of seismic attenuation, why seismic attenuation is one of the least understood physical mechanisms, practical takeaways from her lecture, and highlights from two real-world case studies. This episode is sponsored by TGS. TGS offers a wide range of energy data and insights to meet the industry where it's at and where it's headed. TGS provides scientific data and intelligence to companies active in the energy sector. In addition to a global, extensive, and diverse energy data library, TGS offers specialized services such as advanced processing and analytics alongside cloud-based data applications and solutions. To watch Nimisha's course today, visit sug.org/podcast. Now, for our conversation. Your honorary lecture is called Understanding Seismic Wave Attenuation Mechanisms in Porous and Non-Porous Media, Some New Insights. What did you want participants and future participants in listening to this talk to take away about seismic attenuation?
So, as my talk is already loaded on the SAG website, but I can give you a brief overview. Like as I mentioned in the talk itself, that it's not like a very theoretical talk or on the because this topic is very fundamental and very basic concepts are being discussed. But the problem is lot many things unless we use those fundamental things are not clear, and that's what has happened to me, that while working on some real issues I came across the problem of the seismic attenuation, and that's what I started to I started working on the attenuation, and that's what I collected some of my experience from the practical data set and put it in the form of theory, and that's what is given in this HL. It is not really a very fundamental talk on attenuation because lot many people have worked on attenuation problem. Many theoretical papers are published, but this is more like you will get a practical insight into the attenuation problem, that in some cases it might be useful for our work, and in some cases it might be an obstruction to whatever we want to do. So some practical takeaway you can definitely take from this talk.
That is always important as working professionals and students. And one of the things that really caught me in the description of this talk was that you thought seismic attenuation was one of the least understood physical mechanisms that affect the seismic wave propagation in the Earth. Why do you believe that?
Yeah, that's really very tricky question and really very good question, I would say. So when I was studying about the attenuation and all, so it looked very simple thing that okay, seismic waves pass through a medium, and after certain distance or after passing through certain medium they will attenuate and all. It looked very simple to me, but the more and more I got into the different mechanisms which are governing the this process, the more and more complications I started getting. So it is not just like one parameter you cannot take just to define the attenuation. Some attenuation processes, yes, like the scattering and all, it's not that difficult. But when we talk about the intrinsic attenuation that is happening because of certain rock properties, then so many factors are there. And if the rock is fluid saturated, then not just rock, the fluid properties are also there. So there are n number of parameters you need to consider to understand the attenuation process. So that makes it little more complicated, and that's why I say that the mechanism that why this is happening is not understood properly, because we have studied certain mechanisms in isolation. Till now, we have not put all them together and try to. Of course, they people have tried, but a clear mechanism putting all these parameters together is still not known. We just see the effect, and then based upon our requirement and our data set, we try to infer certain solutions from that. So exact principle, exact mechanism that why this attenuation is happening in this case is still not fully understood in real cases. In synthetic, of course, yes, you can.
What in particular makes non-fluid related attenuation mechanisms particularly difficult to understand?
So, whenever people talk about attenuation, the first thing comes into, especially if you are working in hydrocarbon reservoir field, the first thing comes into our mind is a porous rock filled with some fluid. So we immediately try to relate this attenuation mechanism to something related that is happening because of fluid. But what if the rock is not porous, it is hard rock? So we think that there is no porosity in the rock. So why a seismic wave should attenuate in such a compact structure where all grains are so compactly closed, and then there is no way to have a porosity where attenuation can happen. So why attenuation should happen in such cases? So that's the more complicated thing. So to understand that attenuation mechanism happening in the hard rock matrix, we have to go into the mineral composition and some other factors, that what is happening inside the matrix. So that makes it more complicated, because you cannot really detect from the seismic or the standard method that why attenuation is happening at that scale. So there is a lot of research now going on in that direction.
What do you consider some of the essential elements to understand rock properties in fluid and non-fluid cases?
So the rock properties, generally what we study are the basic rock properties like velocities, the P and S velocities, density, and of course we do these P and S attenuation measurements also on the rock. So these are the very basic properties that we have to study to understand what are the changes happening in the physical properties in because of attenuation. But if we want to go into more detail, we can get into the pore structure studies also, that how this individual, what is the composition of that rock sample which is being studied, the mineralogy, the mineral composition of that, and then how that is affecting the density and velocity of that rock sample. Then we can understand the attenuation mechanism in more detail.
One of the things you kind of mentioned quite a few times in the talk are these seismic low frequency shadows, or LFS. What causes these seismic low frequency shadows?
That's very interesting question. The seismic low frequency shadows, people have been discussing about this for quite a long time. Means it's not that suddenly this term has come, but the application of seismic low frequency shadows in detecting the fluids in the reservoir has recently become very popular in the oil and gas industry. So what people are trying to see, in fact we have also seen in our research papers, that when the seismic wave propagates from a fluid saturated medium, will the seismic waves will have all the frequencies, and slowly when they pass through the medium, the high frequencies are being attenuated due to the presence of fluid in the reservoir. After some time, when we see the anomalies at below the base of the reservoir, we see in certain frequency spectrum presence of high energy compared to other part of the reservoir. So that type of occurrence of that type of anomaly, that is generally terms as the low frequency shadow, because that we see only in the low frequency band, that can be like 6 hertz, 8 hertz, 12 hertz, depending upon our data set and whatever reservoir we are studying. So in our case, like we have seen at 12 hertz, 14 hertz also, but people do have seen even in lower cases like 5 hertz, 6 hertz also. So basically, it is happening because the high frequencies of the propagating seismic waves are already attenuated, and whatever is left is the low frequency energy. But in some cases, people have also reported the enhancement in the low frequency component. Now that concept is still not understood, that why that is happening. In our articles we have defined that why high frequencies are getting attenuated when waves are propagating through a fluid filled media, but even we could not understand that what is causing the enhancement of some in some cases enhancement of the low frequency component. So that is still the research study going on.
Well, going back to the top, you talked, this is a very practical lecture, and you highlight two case studies, real case studies. And the first one I want to kind of touch on, what role does poroelastic modeling have in your case study exploring the North Sea?
So in the talk, I did not cover much on the real data that poroelastic modeling what we had been using. In fact, the real application we have shown with another model which is called as diffusive viscous equation, so which is little simpler form than as compared to the poroelastic equation. But we have used the poroelastic equation for certain synthetic cases, and if you want to relate it to the direct application of the North Sea reservoir or any reservoir, I can straight away say that in most of the modeling schemes, what people are using is the elastic wave equation, in which people are considering only the rock metrics. The fluid field reservoir, the fluid properties are not being considered. So the moment you consider a poroelastic equation, you have to consider the rock porosity and the fluid field in those pores. So it's a comprehensive media, and the fluid and rock interaction will cause different type of waves, and those waves will also have effect on the seismic attenuation which is being observed when the waves propagate to a poroelastic medium. So if we are able to model that type of attenuation process, that will definitely help in understanding what is happening inside in the reservoir, either because of production or due to injection or due to CO2 sequestration, means whatever reservoir we are studying. So that way the poroelastic model will give you more information compared to the conventional elastic and acoustic modeling equations.
Why is viscoelastic seismic modeling of the Deccan basalt particularly important?
So this is, I would say, a kind of new, very new finding what we have reported in when we started working on the Deccan basalt. So let me tell you, this Deccan basalt study we all started not as an attenuation, means not really a problem where we are going to study the attenuation. We did not even know that Deccan basalt can be attenuating medium. So we were working on this subbasalt imaging issues, and we everyone knows that mapping below the basalt is very difficult because it just doesn't allow to move past seismic waves below it. So mapping the basalt basement is very tricky, and if there are any underlying sediments, there will be a huge impedance contrast, and the energy will not be sufficient to penetrate the basalt and all. So it was all thought like that we should find a method that we somehow ignore the basalt and straight away go to the lower layers, to the sediments and the basement and all. But nobody thought that even basalt can be an attenuating media until we carried out some measurements from the borehole samples. And not all basalts, but some flows we found that the very hard rock which was not supposed to be attenuating medium, but they exhibited very high attenuation of E and S wave in the laboratory. So those results were kind of surprising to us, and then we reconfirmed those samples and all, and then we found that there are some petrological issues, so we had to go in the petrology of those samples to understand that why this rock is altered and why this attenuation mechanism is happening. Now when we proved, means these things are published in our papers, so when we proved that some basalts can be really very attenuating. Now it is not possible for us to consider basalt rock, any model which includes basalt rock using acoustic or elastic wave equation, which is not correct way of modeling. So we had to include the attenuation parameter in the media, because there is no fluid. We have to consider a viscoelastic medium which takes into account the attenuation happening in the basalt. So that's why this we are strongly recommending that, especially for the Deccan basalt. I'm not talking about all the basalts on the earth. There are many large igneous provinces, but especially if we are working for the Deccan basalts, we need to consider a viscoelastic model, not the conventional elastic model. Otherwise, we'll miss on the attenuation part, and we'll always think that basalt is like acting as a very hard rock, and it is just not allowing to pass seismic wave through it. But actually, that intrinsic attenuation is happening in the basalt, and which really needs to be studied in detail.
In putting together this lecture and working on these two case studies, what particularly stood out to you that you really were excited to highlight?
Indian scenario, the Deccan basalts are one of the most interesting geological province which lot many researchers are trying to study for decades. And it's not like that we have even the age of the formation, that what at what age it was formed, even still people are doing research on that. And how many flows we have, even that is not established properly. Every means after every quarter or every 6 months, you see some new findings are coming on the Deccan basalt. So it is really a very hot topic of research. So people are expecting large Mesozoic sedimentary basins below the Deccan basalt, because in rest of the igneous provinces, other people like in North Atlantic volcanic province and all, the hydrocarbon reserves were reported. So similarly here also it is expected. May not be an entire Deccan volcanic province, but at least in the northern part of the Deccan volcanic province. And the total area which is mapped till now of Deccan basalt is 0.5 million square kilometer. So it's huge. So in case we have large reservoirs, so it will be so useful for the country as a energy resource. Now, second thing is, inspired from the Colombian river basalt results, lot of CO2 sequestration studies are also going on for basalt. So basalts are in India are being studied for CO2 sequestration and for energy issues also. So that was the most interesting topic we could take, that okay, let us study the basalt. But when we started studying the basalt, we need to generate certain models, and then we have to see that how seismic data we can make it useful when we go for acquisition, because conventional seismic, everyone knows, that doesn't work in basaltic terrain. So when we started doing modeling and when we carried this lab experiment, as I mentioned earlier, we found these interesting anomalies. And as I mentioned earlier, that we found that for very high density and approximately non-porous samples, the attenuation was very high. So when we brought those samples under the microscopes, we saw some unusual minerals, unusual elements. Means, of course, I can call it minerals in that in the rocks, like chlorophyte and lot of this conchoidal fractures, and some structure which is not generally seen in the standard basalt core samples. So that was one interesting finding we reported, that the mineral matrix, which generally we ignore when we compute the attenuation values for different rock samples. So if we ignore in this case, we are going to miss on the rock matrix attenuation. So that was the most exciting result among all whatever I have presented in the talk. That was the most interesting finding, I would say, we reported.
Yeah, and as you mentioned that response there, for those interested in how this could work with carbon sequestration, that plays a role as well, which is exciting. And I just kind of out of curiosity, why does seismic attenuation interest you particularly professionally?
It really did not interest me. I always saw it as a problem, because
Mm.
when we design an experiment, so we expect that whatever, because I come from an exploration, means the field exploration group. So I'm heading that a group which is dealing with the coal and shale gas exploration programs in India. We are acquiring lot of data and all. So when we design an experiment, we expect that whatever seismic energy we are impounding, we use these heavy vibrators. So it is expected to reach the target, but it doesn't. So we try to model different scenarios, that how we optimize our energy source so that it illuminates the targets properly, and our all the receivers along the lines are properly receive proper signal and all. So but because of this attenuation problem, it doesn't happen. So in lot many cases, including this basalt terrain, and then we had been acquiring data in many coal fields, where there are sequence of coal seams in from very topmost layer to target layers and all. So all those coal seams are also highly attenuating medium, and they are not allowing seismic waves to pass to the targets. So that's how, when we saw that this that we need to optimize our acquisition, we started looking into different attenuation processes, which is not allowing us to work properly. But the more and more we started looking into that, the more and more interest I got into the attenuation problem. And then I did not see as an obstruction. Rather, we when we worked on this North Sea reservoir, we found that even this mechanism can be very useful to detect CO2 anomalies in the reservoir. So in some cases it is useful, and in some cases, yes, it's a problem for acquisition. So that's why I got interest that it's really tricky that in which area you are working, you must be happy to see an attenuation, and you might be really unhappy to see, oh my god, all these waves are attenuating, our targets are not illuminated. And one more thing I would like to add here that we did some study and we found that lot many parameters that we measure, especially in the reservoir like velocity and all, these are not that sensitive to the changes in the fluid. Of course, they are sensitive, but if we compare with the rate of change in attenuation, then the rate of change of these property is less. So, if somehow we are able to quantify the attenuation happening in the presence and in the absence of the fluid, then we can quantify why this attenuation is happening and how much fluid is changing in the reservoir. So if that type of study we are able to do, it will be really, really useful in lot many time lapse cases that includes the NECO2 sequestration project also.
Well, that's a good lead into the last question here, as you just kind of used your curiosity and trying to solve a problem to look more into seismic attenuation. And you yourself, you've written dozens of articles. You've won numerous awards. You're currently right now the lead coordinator for an upcoming theme around sequestration and enhanced oil recovery. What one piece of advice would you offer someone looking to succeed in this field?
Let me tell you one thing. Probably for geophysicists, if you are asking like the someone to lead in this field, mostly from the geoscience or geophysics background, maybe this COVID time is not really good for people who are in geophysics field, because in last 1.5 year I received so many mails from students who are getting frustrated with this COVID situation, and the oil industry is not doing good, and lot many means people are really feeling sometimes hopeless with this the way things are happening right now. But this is again the appropriate time to answer this question also, because many people think that geoscience geophysics is just oil industry, but that's not true. There are lot many other branches of means where you can apply for, where you can get jobs and where you can make your career, like geotechnical engineering. Lot of infrastructure is coming on that is not going to stop, whether it is pre-COVID era or post-COVID era, whatever it is, the infrastructure is going to grow. So there are a lot of geotechnical applications coming where you will be required to give the subsurface structure in terms of shear wave velocities and other parameters. So that way one can build career in that. Then in the countries like India, where there is lot of scope to work on the unconventional energy resources. I mean unconventional means like coal bed methane and shale gas, where absolutely no work has been done when it comes to like reserve estimation and how much resource potential we do have. So there is lot of scope to work in the unconventional field, where it can be also seen as a cleaner fuel compared to the conventional hydrocarbons. And even if we talk about the conventional hydrocarbons, the world is not going to change means very fast. Means whatever changes people are expecting, it will be a gradual change from conventional fossil fuel to green energy, and that should happen, because as a geoscientist we all have responsibility that our earth, our environment should be clean, and we should have minimum carbon footprints as possible. But still it is a gradual process. Suddenly oil industry is not going to shut down. So still we have good scope in the oil and gas industry, in the unconventional, in geotechnical. Then not many mineral exploration industries are also looking for geoscientific application. We can make good career there. And on top of that, lot of societal problems like sea saltwater intrusion in lot of coastal areas, groundwater exploration. So a lot of water science issues can also be solved using geoscience and geophysical applications. And in of course in the archaeological field, the geophysics finds this wonderful application in archaeology. People have not ventured much into this. And as we discussed so much about the CO2 sequestration and all, we always have a role to play in the climate change problem if we are talking about the CO2 sequestration issue. So there are n number of fields we can work on. So there is no need to get demotivated at this situation that oil industry is not doing good and will not get jobs and all. There is lot of still scope to work in field. And of course the fundamental research and the academic positions are always there. Many new universities are coming with different earth science courses, and they are looking for faculties. So we should just focus on understanding the methods properly, and we should try to find out innovative techniques that where we can apply these methods. Then there will be always a scope for a geophysics to work.
Well, that is, I'm sure, very encouraging to hear for many people out there. So thank you for that nice reminder. And thank you for putting together this talk. It's a lot of interesting things to talk about and a lot of future looking things as well. So thanks for sharing with us a little bit this evening and for putting together this lecture.
I enjoyed talking to you so much. Thank you so much.
Thank you for listening to SEG's flagship podcast, Seismic Sound Off. SEG produces these episodes to benefit its members, the geophysics community, and inform the public on the value of the science. To show your support for the show, please share this episode with a friend, colleague, or a manager that would enjoy hearing this show. Your recommendation is the single best action you can take on behalf of SEG's podcast. To receive the latest episodes first, follow Seismic Sound Off on Apple Podcasts, Spotify, or Google Podcasts. Original music by Zach Bridges. This episode was hosted, edited, and produced by me, Andrew Gary at 51 Features. The SEG podcast team is Ted Bakamjian, Kathy Gamble, Allie McGinnis, and Mick Sweeney. Thank you for listening. This is Seismic Sound Off, signaling off.